All right, so we have chapter 3 today, and chapter 3 is on vectors and coordinate systems, because this chapter basically prepares us to start treating everything like vectors and understand how we can work with vectors. We can represent vector in graphical and graphical method. Also be able to calculate vectors, in a way like, let's say, adding vectors together, multiplying vectors together, or, scalar times a vector and all those things. So chapter 1 and 2, we already, been working with vectors. We already, hopefully at this point, you guys understand what the vector is or what the scalar is. We're going to, again, summarize all of those quantities and mostly look at in terms of how we can work with vector addition, because vector addition is relatively, abstract idea, and it's not like 3 plus 2 type of thing. It's when you're adding two vectors together, you have to look at in terms of, are they one-dimensional vectors? Are they parallel to one another? Are they perpendicular to one another? Or, let's say if they're not, then there are ways that we can, work around to add vectors together. And it's never as simple as just, adding, one vector magnitude plus another vector magnitude. It only works in a very, limited cases. In any case, so what I have here is we have, several quantities, two types of quantities that we're going to be working with. A scalar quantity, which we talked about, right? So the scalar quantity is like mass, a temperature, volume, speed, a distance, right? All of those things are, a scalar quantity because they describe something that has only a number associated with the unit. So for example, 20 kilograms or 30 Fahrenheit, those are things that, you can use to describe mass and temperature. You don't need anything else. You don't say it's 20 kilograms north or, 30 degrees south or something like that, right? 30 Fahrenheit south. So those things basically are number plus a unit, can be positive, can be negative, can be zero, because you can have negative 30 Fahrenheit, right? For example. So, but they are basically not directional. And then we have other quantities that are directional that require magnitude and direction. And those quantities are going to be, the ones that we're going to concentrate most in this chapter. And we're going to be learning about all of those. And in a way, it's going to prepare us for chapters 4, 5, 6, right? All of those chapters then use this vector concept that we're going to be learning. All right. So you can see, right, the geometric representation of a vector, because we can represent any quantity that is a vector with an arrow like this. So you can see it's an arrow with the tail of the arrow placed at the point where this measurement is made, because let's say what we're saying here is this, vector, which is, let's say in this case, velocity, is only at that instant of time, that position, okay? So even though it's this long, doesn't mean it goes all the way from here to there, because when you're here or when you're there, you might have a different velocity vector. The idea is that this vector represents, what is the velocity at that, where the dot is at that point. All right. So then we label the vectors by drawing a small arrow over the letter. So let's say here I can say that there's a, put it like this, arrow over the letter, right, to represent that it's a vector. Again, that is a notation when you draw that small arrow on top of a, let's say the letter that we have for the vector. So for example, if you have a vector A, this can represent a vector like this. Now, sometimes I've seen students, when I have a vector in the opposite direction, they would put vector A now in this direction. No, this is wrong, because, yes, the actual vector now is to the left, but vector A, to represent that it's a vector, remember, this is just a notation. This is basically how it works. Just like, let's say if you're writing V initial for a vector, if the vector is to the left, you don't write V initial over there, right? So this is just, again, just a notation. It's always on top, that, little arrow pointing to the right. But in any case, so vector is a quantity that has magnitude and direction. So it has two things. Magnitude represents its size. For example, here it's 5 meters per second for the velocity. 5 meters per second, how fast it's going. That's the magnitude. And then you can have a direction. So let's say here you can see, right, with the arrow on top, this indicates that, well, actually I have to go back and change that, because this is just a magnitude. If I'm putting magnitude of the velocity, then I just put v without an arrow on top. So that's the magnitude of the velocity. So direction and magnitude. So let's say here's the velocity vector. Generally, here's the magnitude, and then you have a direction. So now the direction can be described in a number of ways, okay? So there is no, let's say, right or wrong, because we can use any type of coordinate system technically to describe direction. Let me show you, for example. So let's say you have a velocity to the right. Well, I can say it's in a positive x direction. Or I can say this is basically east, right? That's also correct. Or I can say then the angle here is 0 degrees. That is also correct. That means this is the magnitude, and those are three different ways I can represent the direction of this vector to be in a positive x direction. Plus x means positive x direction, east means positive x direction, theta equals 0 degree, again, means positive x direction. Then you will see that we are, have a freedom, right, to do this, but there's a little bit better way of representing direction, which is using a unit vectors, and we will learn that also in a little bit. All right, so let's start with the probably simplest, vector, because it's a little more obvious, it's easy to visualize it, and that's the displacement. So we already talked about displacement in chapter 2. Now let's talk about, a displacement, and maybe displacement versus distance. That's, also an important thing to understand. So let's say here we have, let's say suppose Sam starts from his front door, takes a walk, and ends up 200 feet to the northeast of where he started. Okay, now that means I can take a coordinate system and I can kind of write it like this, where I take his starting point to be the origin. And then let's say now, I can say that, let's say this is point A, and I can take this to be point B. Point A, point B, and that's basically the displacement of Sam. The displacement is a straight line connecting your initial and final points. Okay, now 200 feet represents this direct distance from A to B along that line, which we're gonna label it as S with an arrow, means it's a vector. So 200 feet is the, let's say the size of this vector, right? And then we have a direction, northeast. That means we take this to be east, we take this to be north. Technically, if it's a northeast without any angles, it means this is exactly between north and east, so it's 45 degree with respect to, let's say east, or with respect to north. Generally, you can say 45 degrees northeast or north of east. North of east means basically northeast. Or technically, it also would have been 45 degree east of north, right? Would have been exactly same vector. But you can see, right, this is how we would write this vector. And it's a, displacement vector. You can see, right, this is how you represent the magnitude without an arrow, or this is another notation for the magnitude. So kind of like absolute value of the, vector S. So this is 200 feet, basically the length of that arrow. Now, how about the distance? Well, the distance, could be different because, for example, distance is how many, steps or how many meters Sam took to get to that point B. If Sam moved along that vector S, then he probably had a distance of 200 feet, which is, equals to the, the magnitude of the displacement, right? But look at the, this dashed line. You can see, right? Probably he went like this, right? He went like this to get to point B, and you can see he probably moved, greater distance than that 200 feet. That means distance is just basically how much you move, right? So how much you move compared to, let's say, how far away you end up relative to your, initial point. So how much you move, and this could be just basically, let's say every step is 1 meter, right? So just counting number of steps. So let's say maybe let's say 300 steps or 300 meters. So that's the distance, okay? So distance, is either equals to the displacement or is always going to be larger than the displacement. Also, the distance can never be negative. Distance is just basically once you start moving, doesn't matter in which direction you're moving, your distance is always a positive quantity. Magnitude of any vector is also a positive quantity. Okay, so magnitude of any vector is also a positive quantity. That means you just represent the size from between A and B. Then, the difference here is that distance is a scalar quantity, where the displacement is a vector quantity. Okay, and if you think that, for example, that the distance is the magnitude of the displacement vector, that would also be wrong, because you can see, right, 200 feet is not the distance. Distance is maybe, like, let's say I'm estimating maybe like 300, right? And you can see, right, it's much more than size of this vector. Okay, so again, if, for example, Sam would go in a straight line like this from A to B, distance displacement would be the same. But you can think of like this distance displacement always either the same or distance always greater, but they're not necessarily the same thing. All right, so now one thing we can have is this. Let's say you have a neighbor, Sam has a neighbor, Bill, and they both walk 200 feet to the northeast of their own front doors. So I take Bill's displacement to be a B rather than, let's say, S that we had for the Sam, and this is 200 feet northeast. That means with respect to his own front door, right, which is right here. So if I do this coordinate system, then this is also 200 feet. Let's say going from A to A prime, let's say, to B prime, right? So let's say he also goes 200 feet, also goes northeast. So if I comparing vector B and vector S, I can see that both of them are 200 feet long. Both of them point in the same northeast direction. So then we can say those two vectors are identical. They are exactly the same magnitude, exactly the same direction. That means you can have any two vectors, right? Here's vector A, here's vector B. If they both point in the same direction and both have the same length, then you can say they are exactly the same. All right, so let's say, for example, maybe B is in the opposite direction but has the same length, then you can say A is equal to negative B, that negative indicating that, opposite direction, for example. All right, so now let's look at what we can have in terms of, let's say, Sam, let's say, for example, Sam, if he didn't stop, moving, but continued, let's say, moving, and he would have been able to maybe have a second displacement and have a second, a vector, and we would have been able to maybe add them together. So let's look at something like that over here. So let's say then you have a hiker, and hiker has a displacement such that he moves 4 miles to the right, which is basically east. So this is, this is the starting point. So 4 miles east, we represent it as with vector A. And then 3 miles, so 4 miles east and 3 miles north. Then this is then that vector. All right. So then what we do with that information is this. So let's say then, what would be the displacement of this hiker? Well, hiker's displacement, if you're trying to, let's say, understand in terms of where is the position of the hiker, let's say, relative to where it was before. So that's kind of what displacement is. Where are you right now compared to your starting point? So let's say this is the end point, that's the start point. Now, to find then, the displacement, it will then be requiring us to do the vector addition. That means you take vector A and add vector B to that. All right, so we know that vector A has a, so for example, I can say that vector A is 4 miles, and let me put it like this, right? Let me put it like this. So this is basically in a positive X direction, and then vector B is then 3 miles, and this is in a positive Y direction. Those two things, information that I have. You can also say east and north, right? So then, if I want to find then the displacement, the net displacement, then I cannot just come here and say, all right, so it's 4 miles plus 3 miles, then get as a, let's say, 7 miles. All right, so 7 miles as my, for example, the displacement. All right, so this would be wrong. That's the reason that it's wrong, because those two vectors, A and B, they're not on the same axis. All right, so let me basically explain in terms of when you can actually algebraically add those two vectors together. All right, So for example, let me go back here and just give you that example before going back. So let's say if this is being your starting point, let's say that vector A was here. Here's vector A. But then vector B, instead of heading north, let's say again continued in the same direction. So let's say this would have been vector B. That means I would have had vector A as 4 miles in a positive x direction, and vector B is 3 miles in a positive x direction. Okay. Then to find the net displacement, all right, net displacement, it would have been, so this is your starting point, right? So this is your end point. Then I would basically try to see that what is the net displacement from your start point to end point. And again, that would have been vector sum of vectors A and B. All right, so but this time, what I have is this. Those two vectors, A and B, are on the same axis. That means both of them are horizontal. So in this particular case, I can say, all right, so this guy here is 4 meters, right? Vector A is 4 meters. Sorry, 4 miles. Then, let's say plus x, right? Direction in terms of, then plus vector B, which is 3 miles plus x direction. And since the x direction basically match for both of them, right? The directions match. Then I can just say this is basically 4 miles plus 3 miles in x direction, in a positive x direction. And then this vector sum would have been 7 miles in a positive x direction. So magnitude 7 miles and plus x is the direction. Now, if I add those two together, I generally get a new vector. Let's call that vector C. Vector C would be a new vector, which then will have 7 miles as the magnitude and plus x direction as its direction. And the way I can represent that vector C, it will be connecting your start point with your end point. As you can see, right, kind of like this. If I connect those 2 points, I get that blue, which is, let's say, this vector C. All right. So let's say if I look at that vector C, I want to see, does it match what I calculated? Well, I can see that length of C is kind of like same as A and B combined. So that means it is 7 miles, so it is consistent. And the direction of vector C is basically also to the in a positive x direction. So the direction also is consistent. That means I have a vector C, which is 7 miles and pointing in a positive x direction. That means I can algebraically add two vectors together only when they're on the same axis. Same way I can do this, for example. Here's a vector A. Well, this time vector A is vertical. So then what I have here is, let's say this is my start point. So, and then from, let's say this is 3, and I get to this point, and then I have another vector, vector B, which is like this. So here's vector B. All right. So now, one thing I can see is this. Vector B is about half the size of A. So it is, let's say, consistent if I would put 1.5. It's basically good estimation. Also, vector B pointing down instead of up, so it is also then negative. That means what I have here is A and B are two vertical vectors. So if I do then vector sum of A plus B, which is equals to vector C, what I will get here is this. So this is 3, let's say in a positive y direction, plus this is 1.5 in a negative y direction, right? So then that negative goes in front, so becomes 3 minus 1.5, but both have a vertical direction, right? If I calculate this, this will be 1.5 in a y direction. So positive 1.5 in a y direction. That means if I connect my starting point with my end point, which is here, right, my end point, then this is the resultant vector, which is vector C, which has 1.5 as a magnitude, which is consistent. You can see, right, 1.5 is about half of, vector A, and it's in a y direction, positive y direction. Again, that's consistent with that. That means you can add or subtract two vectors together algebraically if they're on the same axis. Two horizontal vectors, two vertical vectors, two vectors in the z direction, As long as they're on the same axis, you can do that. So technically think like this. If vector A and B are parallel, by parallel, I mean, like, let's say they're on the same axis, or, up, same direction or opposite direction, right? So, and means that, you can algebraically add them together. This particular example, we have this. A is in a x direction, positive x direction, B is in the positive y direction. So I cannot add them together anymore because there's like apples and oranges. So A is apples, B oranges, right? So I cannot add them together algebraically. So this, just directly adding them together doesn't work anymore. But we have a way of doing that, because one of the things you can see here is when I have vector A, then vector B, then I get to my final point, then my displacement vector C is a vector connecting those points A and B, which is this vector over here. Once I construct that vector, then it is clear to me that A and B are perpendicular, two perpendicular vectors, and then vector C, basically when it connects start and end point, you end up with right triangle. So then what I can do here is I can understand this, that if I have a right triangle, then this 4 miles, which is size of A, 3 miles, which is size of B, can be used then to find this, C, which is size of, vector C, which is basically, in this case, you end up with, you have adjacent side, you have opposite side, and this is hypotenuse, right? That means you can use this triangle using the Pythagorean theorem, right, to calculate the size of the hypotenuse, which is basically magnitude of vector C. And then you can even the direction, which will be some angle theta using polar coordinates, right, for that vector. So that's why using the sides, right, if you remember, right, so let's say hypotenuse square is equals adjacent square plus opposite square, right? Right, so that means, C square is equals to A square plus B square. That means, I can use then this equation to calculate the size or the magnitude of vector vector C. That means vector C is my hypotenuse, which basically means that Pythagorean theorem, can allow me to calculate the size of, the hypotenuse, which ends up being the magnitude of vector C. And in this case, what I will get here is 5 miles, which will be the correct, answer to that. So 5 miles is the size of vector C. And then we can use this inverse tangent, right? Which will be then inverse tangent of opposite over, adjacent. Opposite is B, adjacent is A, so 3/4, and we get 37 degrees. Then I can say when I'm adding those two vectors together, A and B, if those vectors are perpendicular to one another, then technically I can use this approach. I can use the Pythagorean theorem to find magnitude and the direction of the resultant vector, which is vector C, right? That means what we did here is we learned 2 ways to add vectors together. Algebraically adding vectors together is possible if they're, parallel on the same axis. Using Pythagorean theorem, it's possible to find the resultant and magnitude of a vector that is, let's say the sum of 2 perpendicular vectors. Okay, that means when you're adding vectors together, see A plus B, we already can see that there's 2 different, ways of doing that depending on their relative direction of A and B. Okay. Well, we're not done yet. You can actually, have another example where then A or B, neither parallel or perpendicular. Then you have to actually use completely different method, which we will, also learn in order to kind of like get the resultant in terms of its magnitude and direction. Okay, but let's first learn a graphical way that we can add any 2 vectors together, or technically any 3 vectors together, or 4 vectors, 5 vectors. But let's, sort of like, let's take a, let's say 2 vectors. In this case, I'm going to take vector D and vector E. I have 2 vectors. And again, those are anything, it can be anything. That can be 2 displacement vectors, can be 2 velocity vectors, can be 2 acceleration vectors, right? Anything there is a vector. So I have 2 vectors, E and D. And one thing I can do here is, so let's say if I have this vector E, See if I move it anywhere I want, as long as I keep the same size and same direction, is the same vector. Remember that Sam and Bill, right? Dot vector B and S, as long as they were exactly same direction, exactly same size, they were exactly same vectors. So for example, then I have these two vectors and I want to add them together. What is D plus E? Okay. Graphically, I can use two methods to do that. Here's the first one, known as a tip to tail, which means that you take the second vector in your sum, which is E, and you move it so that tip and tails of the two vectors connect. So then the tip of your first vector connected to the tail of your second vector. That means I take this E and move it here. Okay. Again, as long as you keep the same direction, same magnitude, right? Those two vectors are the same. All right, so let's say we move this here. So that's why tip to tail rule. Once you connect your two vectors in the, let's say the, in your sum, right? Those two vectors connected together, tip to tail. Then you identify your start point and your end point. And then you connect those 2 points. So the start point and the end point, you connect those 2 points, and that's going to be the resultant. Let's call that F. So F is equals to D plus E. And this is the size and direction of this vector F. All right. You're not really getting, let's say, for example, very precise information about that, but still it's an information that can be very useful. And you will see in some of this, calculation, when we solve problems, I will explain. But in any case, that's known as a tip to tail rule. You can also use a parallelogram method, which is basically going back to this, for example. What you do is you connect them at their tails. So you connect them at their tails. And then you construct a parallelogram. So you construct a parallelogram, which is basically the projection of E and D, in opposite sides. And then the vector going where they're connected at their tails, diagonally like this, like here, right? And that's our vector F. So you can see, right? Vector F using tip to tail or parallelogram methods, yield the same answer, same magnitude, same direction. All right. So remember that this parallelogram method is generally good for adding two vectors together. Okay, so you can see, right? You can construct a parallelogram with 3 vectors together or 4 vectors added together. Tip to tail method is a little more, let's say, flexible. I can add more vectors together in tip to tail. So for example, here we have 1, 2, 3, 4 vectors added together. Okay, so I have 4 vectors starting from here. So let's say I have, you can see, right, D1, this vector here. And so let's say this is D1. And then I have another vector, D2. So I move the D2, so its tail connected to the tip of D1. Remember, so tail connected to the tip, tail connected to the tip, tail connected to the tip. That's how it kind of works. So, and then let's say here's D2, and then here's D3, connected tip to tail, and then finally here's D4. And this point 4 here is like, let's say that's my end point, okay? So that means, I add those things together, let's say tail to tip, right? Or tip to tail, right, method. And my DNet, which is the resultant, always connects your start point and your end point. So then this is basically your resultant, okay? This is being the resultant. Then what you can do here is find the size and direction of the DNet using all of those vectors, right? In order to get, let's say, your displacement, if it's a displacement vector. That means you are still adding all those 4 vectors together as vectors, and you can see, right, they are not perpendicular to one another, then they're neither like parallel to one another. So this is a completely different method that we're going to be learning soon. But the graphical method can allow you to add any number of vectors together as long as you connect them tip to tail, and then find the resultant that basically connects your start and end point. How about, for example, how about there was another D5? But D5 then goes from here to there. So let's say this is my D5, for example. So then what is the displacement? What is this DNet? Well, in that case, DNet will be 0, because then my start and my end point will be exactly the same. So my displacement in this particular case then becomes 0. That means for any round trips, you end up with 0 displacement. All right. So these are, some of the, general rules for the vectors. So let's look at here. If you have a vector, you can see, right, representing in terms of its magnitude and direction. One thing you can do here, you can multiply the vector with a scalar. So let's say you have a vector A, which has a size of, I don't know, a size of 5, and the theta here, let's say 20 degrees. Okay. So then if I do, let's say 2 times, for example, right, 2 times vector A, what it does, so because it's plus 2 times, it goes and increases the magnitude. So it makes it double. So this becomes 10. Because this is plus, it doesn't change the direction. So this is still 20 degrees. So you can see, right, then B is equals to C times A. So then it's a, twice as long, vector pointing in the same direction. Okay. Now, for example, what if I did this? What if I had the vector A, let's say that vector B here is equals to negative 2 times vector A. In that case, then magnitude would double, but then direction, this will change in direction. So the direction would have been, 20 plus 180, right? Basically changing the direction. So then it would have been, 200 degrees, for example. And if you're doing the coordinate system, right, you can see, right, this is then negative 2a, which is twice as long, but pointing in a negative, negative direction compared to a, which is in opposite direction. If you have vector a, if you add that to its, inverse, let's say reciprocal, right, negative a, then what you're gonna get here is 0, right? So vector with 0 magnitude. So a plus negative of a equals 0. Okay. So now, here's what we have. For example, we have vectors a and c. We learned what to do if you have a vector sum of a plus c. You basically construct a parallelogram, and this is the vector sum of a and plus c. So this is a plus c. How about though if you have a minus c? How about that? Well, the resultant in this case, what you do here is this. You change this to this, a plus negative of c. That means you take your vector a, right? You take your vector a, but this vector c here is changed direction. So then this will be your vector c. And then the resultant will be this guy here. So you can see, right? So kind of close enough. So that means a minus c is same as a plus negative of c. And then you can still use the tip to tail method or parallelogram method to construct that. All right, so you can see, right? So this is then parallelogram method of that, where, instead of tip to tail, you connect them at tails, and then, create a parallelogram, and diagonal line will be your resultant. All right. Here's an example. So you have a postal employee drives drives a delivery truck along the route shown. Determine the magnitude and direction of the resultant displacement by drawing a scale diagram. So approximately so. All right, so let's say it's, it's 2.6 kilometers. And you can see, right? So you can say here's vector A, and this is 2.6 kilometers, and I can say north as a direction. And then after that, 4 kilometers east, so using this as a coordinate system, right? So here's vector B, which is 4 kilometers, and this is east. And then what we go here is we go from here to, 3.1 kilometers northeast. So let's say here's vector C. So this is 3.1 kilometers, and this is northeast, north of east or northeast. Now, what is the displacement? All right, so the displacement will be connecting your start and your end point. So let's say if I go and if I use this, so the displacement will be basically this vector here. All right, so this is our, let's call this R as a resultant. And as vector, this is basically A plus B plus C. All right, so remember, I cannot just add there, I cannot just do this 2.6 plus 4 plus, let's say, 3.1 to find the magnitude. You can't do that because, they're not on the same axis. If I had just those two, I could have just use a Pythagorean theorem to find the resultant magnitude. But it's also, I have, they're not perpendicular to one another. I have also this vector C. That means what I can do here is I can estimate maybe. I can estimate in this case. For example, I can estimate that size of R, you can see, right, is longer than any of my vectors. And if I take this to be 4 kilometers, right, you can see, right, if I take this to be 4 kilometers, then I can maybe can see that this is probably about double that length. See, vector B is 4 kilometers and vector R is about double that. So I would estimate maybe this to be, I don't know, maybe let's say 8 kilometers. Again, I'm estimating. Then I can see that it is less steep than vector C, and vector C has 45 degrees, but it's less steep, right? You can see that from the shape. So, but it's not by much. So then I can estimate that the direction of this to be, I don't know, maybe 35 degrees. All right, so a little bit less than that, so maybe 35 degrees. Again, you can estimate slightly different, maybe plus minus some values, right? Remember, there's uncertainty in any measurement. And I imagine my uncertainties is plus minus 1 for the magnitude and plus minus maybe 5 for the angle theta. Could have been 40, could have been, maybe not necessarily down to 30, but at least it would have been, let's say, between 34 to 38, maybe 33 to 30, to 40, something like that. So maybe plus minus 4, something like that. Right. So what it means, for example, the graphical method that I just used is a tip to tail method, obviously. It allows me to estimate things. Okay, it allows me to estimate things. And if I put a coordinate system here, I can also see this vector R is in the first quadrant. Okay, it's in the first quadrant. So that's why I could estimate its direction to be 35 degrees. Because remember, all the directions are relative to the positive x-axis. Because if I tell you 35 degrees, you should be then thinking of counterclockwise, 35 degrees above the positive x-axis. If I tell you 35, you're not going to go to the negative y-axis and go clockwise 35 degrees, right? You would never do that because the standard here is take this positive x-axis as your reference, and then your theta increases counterclockwise. So if it's 35, it's counterclockwise from positive x-axis. And that's generally how we, use as, as a standard for all of those type of, calculations. So that's why these quadrants in a Cartesian coordinates become very important. So for example, here you can see, right, this positive x-axis is my, reference line, and my theta now increases counterclockwise from 0 to 90 to 180 to 270 and then to 360 and then so on and so forth. Okay, that means I can use the Cartesian coordinates, right, and along with polar coordinates to represent the direction. For example, if I tell you there's a vector B with the angle of 90 degrees, you know what that vector is, right? 90 degrees means that that vector here is along the, y-axis. This is a vector, 90 degrees. If I tell you there's a vector of 190 degrees, you also know that where it is, right? So this is a 180, so maybe like this. This is 190. If I tell you a vector negative 25, hopefully you again know where it is. Negative 25 means clockwise with respect to, if I don't give you any, let's say, with respect to negative x or with respect to negative y or positive y, then you automatically should be thinking of with respect to positive x. Negative 20 means clockwise, right? 20 degrees. That's my negative 20. Okay. Now, one of the things you should remember about this, Cartesian coordinate system is that generally we take quadrant 1 to be positive x and positive y. That means x is positive, y is positive, sorry. Quadrant 2, we take negative x, positive y. That means any x or a component of x is going to be negative, y, anything related to y is going to be positive. Quadrant 3, negative x, negative y. Quadrant 4, positive x, negative y. Okay, so they're reciprocals, right? There's a symmetry, nice symmetry that you guys can remember. And this is going to be important, especially when we get to the like let's say the next slide, because next slide is an example. For example, let's say when you're adding two vectors together. So let's say here's a vector. Let's say here's vector A. And then, for example, here's vector B. And I want to add them together, vector A plus B. How do I add them together? I can't use the methods that I just learned, right? I cannot just algebraically add them together. They're not on the same axis. Those are both of them each one two-dimensional vectors. They're not even perpendicular to one another. Again, I cannot use Pythagorean theorem to find the resultant. I can use the graphical method. Here's the graphical method, right? So I can say, right, okay, so here's a parallelogram, and this is the resultant. This is good because I know that this resultant in the first quadrant, I know that basically it's probably a little bit longer than vector A or B, and it's probably have a roughly 45 degrees. I can estimate those things, but I want to find everything more precisely. I want to find the exact length of this resultant vector, let's say R. I want to know its exact direction and things like that. And in order to then do this, you can see, right, because A and B neither perpendicular or parallel, we need to then find a new method, new way of calculating the resultant using vector A and B information. Because A and B, as a two-dimensional vectors, we assume that we're probably given their magnitude and the direction relative to, let's say, my coordinate system. And then I can use those information then to find this resultant R. So let's look at this two-dimensional vector A. That means for now, just ignore everything else, but just look at that two-dimensional vector A. That means, let's say we're given that vector. Okay. Now, generally, anything two-dimensional, let's say we have two-dimensional vector, and if you add that two-dimensional vector to another two-dimensional vector, let's say, I don't know, like I showed you, like let's say another vector B, you would never be able to directly do that. Okay, so you can't just add their magnitudes and things like that. So it's a lot more complicated. The easiest thing would be to find what we call components of this vector A. So for example, you take this vector A and find its projection, right? Or it's what we call component along the x-axis, which is, let's say, this vector over here. You can say, right? So it's projection or shadow or component on the x-axis. Same way we do that for the y-axis. So this is basically its projection on the y-axis. Okay. Then what we do here, so basically, you can see, right? We can see that what we constructed here is a parallelogram where AX is one vector, AY is another vector connected at their tails. And if I use those two to construct a parallelogram, then diagonal line, which is end up being vector A, is nothing but the sum of the X and Y components of this vector A. And this is important because if you have a vector A, you break it down into components, you're basically creating two other vectors out of this one two-dimensional vector A, okay? But they are related. They are related in such a way that vector A is equals to the sum of vector A and B together, okay? For example, think like this. So if you start from here, let's say think like this, 4 meters, right? Going to the right. So let's say this is A, and then you go in this direction, and this is vector B, right? So you can see that, and let's say this is 3 meters. If I go along the A vector, then along the B vector, I'm gonna get to this point over here, right? Where my end point is. Let's say this is my start point. That means if I have A and B together, I end up at that point, at the end point. But I can also go straight from the start to end along this, let's say vector A, or, let's say, which means that what I have here is those two vectors together, right? I should have put like AX and YY, sorry guys. So those two vectors together, right, is basically equal to the parent vector. But you have to add those together so then their sum is equal to the parent vector, right? So, which means that any vector A or any vector B, right, any two-dimensional vector can be replaced by the sum of their components. So that's why we're saying that this vector alone is equivalent to the sum of its components, okay? That means then I can take that AX and AY and replace vector A with those two. Now the question is that why would I want to take one vector and replace it with two vectors? Well, the answer is very simple, because those two vectors AX and AY are both of them individually just one-dimensional vectors. AX is, constrained along the x-axis. AY is along the y-axis. That means x component of any vector will be either to the right or to the left. Y component of any vector either going to be up or down, basically, along the, let's say, positive y and negative y. So that's why what we do, we have broken A into two perpendicular vectors that are parallel to the coordinate axis. That's the thing, parallel to x-axis, parallel to y-axis. Okay, that means we are replacing vector A, which is two-dimensional, with two one-dimensional vectors. This is known as decomposition of vector A into component vectors. And this is very useful when you're adding two vectors that are basically two-dimensional. It could be even three-dimensional. That means anything that's a little more complicated than adding two parallel vectors or adding two perpendicular vectors, we have to go through this approach. We have to decompose any, vectors that we are using into their, components. So let's look at some examples. Here's vector A. So now, if you're given vector A, you can see that basically, if you break it down into components, then you're going to have one horizontal component parallel to the x-axis, one vertical component parallel to the y-axis. So in this case, for example, if you have a vector A, right, you can see, right, if I break it down into AX and AY, and remember, vectors are independent of the coordinate system. I don't necessarily have to take that vector A and, start from the origin. I can start it anywhere I want. So think like this, if I break it down, I'm going to get this vector AX, which I can say is 1, 2, 3 meters. So I can say AX is plus 3 meters. Plus 3 means 3 meters magnitude plus in a positive x direction. Then AY starting from here is 1, 2. So it's plus 2 meters. 2 meters is magnitude, plus is the upward direction. That means what I have here is the vectors AX and AY replacing basically the resultant vector, which is vector A, right? Because think like this. So if I have this AY axis, this is AY, and this is AX. See, if I construct a parallelogram, this is the resultant. Now, one thing you will see is this. I can remember, take this any vector and move it around, and I'm going to take vector A and AY and move it here. Once I move AY, to that position, you can see basically I have nothing but the tip-to-tail method of connecting AX and AY. Then I can say vector A is equals to AX plus AY, right? AX and plus AY. So there are a couple of things you can do, right? So you can see that you took a vector A and broke it down, and then you have basically, its components AX and AY. Okay. So from here, then you can see that since the vector A is in the first quadrant, then if I break it down into components of AX and AY, the components of this vector A, since this is in the first quadrant, should be positive X, positive Y. And this also should match in which direction I have those vectors. If you look at AX, it is indeed pointing in a positive X direction. AY indeed pointing in a positive Y direction. Because if you have a parent vector in very specific quadrant, it should still follow those quadrant rules that we learned a few slides ago. All right, so that's kind of what we have over here for vector A. So we can describe each component vector with a single number called the component. So let's say the component tells us how big the component vector is, and with its sign, which ends of the axis the component vector points. So let's take this vector B then. So vector B, if I break it down into component, so this will be, let's say, so this is its shadow along the x-axis, so that's what I have. So since this is the starting point, I can see that this vector Bx is 2 meters long, so magnitude is 2 meters. Then if I, do the shadow along the y-axis, I can see that this guy here is also 2 meters in terms of its magnitude. Okay, but then I can see this. Vector B is, technically pointing toward the second quadrant. So Bx should be negative and, should be pointing to the left, and it does. So then Bx is negative 2 meters, negative indicating it's pointing to the left, and By is positive 2 meters, indicating that pointing upward. That's why, again, remember the second quadrant, right? Plus y, but minus x. That means positive y-axis and negative, x, or sorry, positive y component and negative x component, which basically, again, matches the sign of x and y. All right, so if you have a vector A, one of the things we can do here is we can use absolute value ax of the x component. So we can say that this is equals to ax plus ay. Then if I take then a vector ax, then I can use this, let's say notation to present the magnitude, right? But I just use ax, let's say. That's its magnitude. Remember, it's always going to be pointing in plus minus x direction, depending on which, quadrant it's pointing. And then you have this vector ay, which has a magnitude of ay, and it's always going to be pointing plus minus, plus minus y direction. Okay, so that's why the sign of ax is positive if vector ax points in a positive x direction, negative if it's pointing in a negative x direction, but still it's going to be plus minus x. Same thing, ay plus minus y, depending if it's up or down, depending on the quadrant of the parent vector. So let's look at some examples here. So here's like, let's say a vector, and if we can break it down, we can see that, here's the, let's say ax, for example, and here's the ay. So then I can say it's plus 2, plus 3 for the components, because this vector is in the first quadrant, so both of the components will be pointing along the positive direction. Here's another vector b. This will be its y component. This will be its x component. And then if I look at in terms of 1, 2, 3, that's the magnitude of x component. 1, 2, 3, 4, magnitude of the y component. So the x component will be plus 3, indicating that it's pointing to the right. Y component minus 4, indicating it's pointing down, and which matches the plus x minus y for the fourth quadrant, right? Signs of the, components. All right, so now, one other thing I have here is this. So let's say I do have those information. So you can see, right, I have the vector ax and vector ay, or the magnitude and direction of the components. Same thing is here, magnitude and direction of the components of vector b. Can I use the component information then to find the parent vector a? Let's say in which direction is actually vector a is pointing and what is its magnitude? Same thing, can I find the vector b? Yes, we can actually do that. So you can find the components from the parent vector, right? But you can also find the parent vector from the components, okay? So let's summarize that. So let's say here we're given vector A, and what we're gonna do here is we're gonna then assume that we are given, let's say, let's do this. Let's say if we are given vector A in terms of its magnitude and direction. So we're given those two information. That means I know what this vector A is, and I know what the direction of the A is. If I'm given that information, then I can see, right, so this is being vector A, and then let's say this is being the theta A. I can use that to break it down, this vector A, into components. So here's AX and here's AY. What I can see from this is that I constructed a right triangle where AY is basically opposite side of this triangle, AX is the adjacent side of the triangle, and A is technically the hypotenuse. Okay. And I know that I can relate those three things because now what I have again, so this right triangle. So this is the size of AX, this is size of AY, and this is size of A. And let's say this is then theta A. I can relate all of those four things, right, with the, let's say, sine and cosine functions. Okay, so let's say I can see that if I use sine of theta A, this is related to the, if you remember, right, sine of theta is related to the opposite over hypotenuse, which in this case, AY over A. Cosine of theta A is then adjacent over hypotenuse. What is my adjacent here? That's the x component, and divided by hypotenuse, which is A. I also have tangent of theta A, which is then related to opposite over adjacent, which in this case is going to be then AY over AX. So you can see, right, those three equations relate the sides, of the vector A, because remember, we are given vector A and its direction. I want to find the length and the direction of the, let's say the sides. So using then those three, right, sine, cosine, or tangent, I can see that if I rearrange them, right, if I want to find, let's say, AY, I can use, for example, sine of theta, because sine of theta equals AY over A. I rearrange that, then I can get this. AY is equals to A sine of theta, right, by moving A to the other side. And I get another one, which is for the x component, and this will be A cosine theta. That means those two equations will give me the components, the size of the components of AY and AX. And I can also see, is this in the first quadrant? If yes, then both of them are positive. But those two equations, equation 1 and 2, you can say that those are, if you're given vector A and the direction of A, use those to find the components. All right. One thing you should remember here is this. The reason that AY equals, for example, A sine of theta and AX equals A cosine theta, because of my triangle. And if my triangle is different, for example, let's say if my triangle is a little bit different, where the theta is given with respect to y-axis rather than x-axis, then technically my opposite and adjacent side would switch, right? My adjacent and opposite side would switch. That will be, for example, let me show you here. Let's say I have vector B here, but I'm given vector direction B like that. See, if I break that down into components, this will be the y component, dy, and then this will be the x component, bx. Now you can see, right, in this case, sine of theta b is equals to opposite, which is bx, over hypotenuse, which is b. And then cosine of theta b is equals to adjacent, which is by, over opposite, hypotenuse, which is b. So you have to be careful. Is the theta given with respect to x-axis or y-axis? So technically then, your triangle would change and the opposite and adjacent side will also be different. So be careful with that. All right, so let me do this then. Okay, so what we have here is this. You can see, right, this is my vector A. I break it into components, and this is how I can calculate AY. Why? Because theta is given with respect to x-axis. And this is how I calculate AX, again, for the same reason. So AY equals always A sine theta, if the theta is with respect to x-axis. AX equals A cosine theta, if the theta is given with respect to x-axis. So, but sometimes I have this. So let's say if I have a vector that, for example, right, that I'm not given its parent vector. What I'm given here is its components. So let's say I'm given AX. For example, AX here is 5. And I'm given AY. For example, AY here is 4. Then how would I use those two to find the resultant magnitude and direction? That means, how do we reassemble the parent vector from components? Again, we can do that. Because see, if I move AY, if I move AY here, which is, remember, the same vector, then what I can do here is this. So let's see. So then this will be my resultant. This will be vector A, right? So if this is AY, which is 4 moved over there, then that's my resultant. And again, what I have here is, this will be my theta A. In this case, think like this. We are given AX and AY. And we want to find A and theta A. How do we do that? Pythagorean theorem. A is then going to be square root of X component square plus Y component square. And that's how I find that. So you can see, right, square root of 5 plus square root of 4, that will give me then the resultant. So for example, if I do that, 5 squared plus 4 squared, I get 6.4. All right. And then the direction, now I can use any of the sine, cosine, theta function that I just drew. So let's say I can use, inverse tangent of 4 over 5, then to find the theta A. So inverse tangent, 4 over 5, I get 39 degrees. And that's what I have. That means you can reassemble the vector from its components by using this equation 3 and 4. Remember the equation 1 and 2 that I had a little bit a while ago, or this two, 1 and 2 allows you to find the components, and then 3 and 4 allows you to find the magnitude and the direction of the parent vector. Then you can say, all right, here's my vector A in terms of its magnitude, and let's say the direction, okay? So 1 and 2, you are given the A and theta A, use them to find components. Equations 3 and 4, you given a, components, and use that to resemble your parent vector, right? So that means you can go kind of back and forth depending what's given and what you need to find. All right, so, and that's kind of what we have. So this slide basically goes over those things. All right, so, and you can see, right, so one of the things we can do here is this. So for example, if we are adding 3 vectors together, so let's say you have A, B, and C, and I don't know, let me give you like a picture here. So let's say you have 3 vectors, and these vectors can be, for example, here's vector A, maybe here's vector B, and I don't know, maybe here's vector C. And you're adding all those 3 vectors together to get this resultant D. How do we approach this type of problem? Well, the way we do this calculation, right, how we, approach this type of problem would be first do a diagram like this. So then we can see in terms of, let's say, what we're dealing with. You can even then use the tip to tail method to find the resultant vector D. So if you, for example, do A plus B plus C, so let's say you move B right here, so this goes away, and then you move C like here, right, like that, and then you can see, right, this is your resultant vector, right? So that's your resultant vector. And we get some information from that. See, resultant vector is in a second quadrant, right? So it's probably going to have theta of approximately, 100 degrees or something like that relative to positive X. So we get some information. So the graphical method allows you to get some information, but we don't want that. We want actually to be able to find magnitude and direction of this resultant vector D. Well, to do that, we have to first, instead of being able to calculate vector D, we need to be able to find the result, the component of this vector D, the component of the resultant. That means we need to be able to do this. Take each vector A, B, and C and break them down into components. That means every vector is broken down into components, all right? Because what I have is this. If I break down every vector into components and replace those vectors A, B, and C in terms of their components, then what I get here is this. I can actually add all the X components. Why? Because they're all on, on the X axis parallel to one another. So I can actually add all the X components together. And what I'm getting here is the X component of the resultant. Then I can add all the Y components together. And what I'm getting here, I'm getting the Y component of the resultant. So that's kind of what we do, right? So this is a bit different. So I can find component of the resultant vector D by finding the components of each vector, A, B, and C, then adding them together. Horizontal component sum gives me horizontal resultant component. Vertical component sum gives me the vertical component of the resultant. The question is that, okay, so what do we do after that? Well, we just learned, right? If you are given the components of a vector, then vector D magnitude is x component square plus y component square. That means technically all I need here is to find those two guys, and I can find magnitude of vector D. Well, how about the direction? Well, I use inverse of tangent to find the direction of that vector D. That means you can see that you can always find the magnitude and direction of the resultant vector by first finding its components. We're gonna do some examples. You guys will see, like, let's say how to approach all of this. But this is the rough idea. That's why we learn about the components, learn about how to take vector and break them down into components. Because when I'm adding three two-dimensional vectors, let's say, or three vectors together, and they're neither parallel or perpendicular to one another, the only way I can solve this by the component method, using the components of the vectors where all the x components can be added together because they're on the same axis, because all the x components are parallel to one another. All the y components are parallel to one another. And the goal here is to find the components of the resultant. From that, it's easy to then find the magnitude and direction. Same way, if you're subtracting two vectors together, using the component method is also relatively simple. I have the same approach where I find the x and y component of the resultant. And to do that, instead of adding the x components, I subtract the x component. You can see, right? X component of P minus x component of Q. That gives me x component of the resultant. Y component of P minus y component of Q. Why? Because you're looking at the difference between those two vectors. So instead of adding them together, you just subtract. Okay. But again, find the resultant by taking the square root of x component square plus y component square, right? And then use inverse tangent to find then the direction of this resultant vector. All right, so that's kind of what we can do. You can even take a resultant, right, by multiplying some vector by a scalar, which we kind of looked at already. And this will be, if this is a two-dimensional vector, right, if S is a two-dimensional vector, then you can find the component of the resultant by saying constant times x component of the S, constant times y component of the S, and then find the resultant by doing the tx square plus ty square. Find the magnitude of the resultant, and obviously again the inverse tangent. All right, so you can see, right? So in a way, this last approach here is, the last step is the same for all of them. That means our goal is to find components, and then magnitude and direction after you find the components. But that's the thing, that vectors can be relatively straightforward when you have two vectors on the same axis, but it can be relatively complicated when you have like 3 or 4 vectors like all over the place. So this component method allows you to organize your work, allows you to basically take all of those, two-dimensional vectors, break them down into components, and then use the component method to find, your, final resultant vector. All right, so let's look at some examples. Let theta be the angle that vector A makes with the x-axis, measured counterclockwise from that axis. So we're going to find then the angle theta for a vector that has this component, and we're given A, B, C, and D. That means for each part, you have then different components vector. That means we're given, like, let's say vector A, and we kind of like change its direction and things like that. And our goal is to find theta. Let's look at part A. Part A tells us that x component is 2, y component is -1. So, and I recommend always to use a rough sketch. So here's A, here's your coordinate system, and then we're given components. So +2, so 1 and 2, and then -1, so -1. So that's my vectors. So then I can move the y component here. Then my resultant is this guy here. Okay, that means I need to get this theta over here. So this, you can see, right? This is in the fourth quadrant where x is positive, y is negative. Now, I can do this. I can find magnitude of A using those values, and this just will be ax squared plus ay squared, which is 2 square plus 1 square, right? 1/2, which is basically square root of 5. Right, so let's say whatever it is, so the square root of 5, you know, that's the magnitude, meters square, let's say inside it. So then what we do here is, even though we weren't asked to find the magnitude, right? But we can still do that. So let me write magnitude of A is 2.24 meters, let's say, for example. Okay, so 2.24 meters. But the question is to find the direction. And let's define the direction. And what I do here is I use inverse tangent. So then theta here is equals to inverse tangent of y component, -1, over x component, 2. Okay. So what I will get here is then -27 degrees roughly. All right, so now, what does it mean -27? It means 27 degree clockwise from the positive x-axis. Generally, when I'm asking for the direction of a vector, I want this theta relative to the counterclockwise from positive x-axis. So what we do here is then, for this particular case, we know that full circle is 360 degrees, and this is 27 less than that. So then technically then theta here is this, 360 minus 27, so it's 333 degrees. That's going to be then the answer. That's the direction of this vector A, because we're taking with respect to, counterclockwise with respect to positive x. Part B, ax is 2, ay is 1. So that's a little bit easy one, because you have 2 in the x direction, y in the y direction. Both of them are positive. So my resultant is this guy here. Okay. So will I get a different magnitude for vector A? No, I'm going to get the same 2.24 meters. The direction now in this case will be inverse tangent of 1 over 2. And this just give me 27 degrees, let's say. I'm rounding, so 27 degrees. And this will be already this guy here, so it is with respect to positive x-axis, counterclockwise, so we're done. Okay. How about for part C? For part C, I have this. I have -2 for x and +2 for y. So -2, +1 for y. So then my angle here is this guy, right there, because it's a second quadrant vector. So magnitude still going to be the same, because x and y components are the same. Remember, even if you have a negative or positive, you are squaring those values, right? So you're squaring those values, so you're going to get same for A. But theta will be inverse tangent of 1 over -2. And what I'm going to get here is I'm going to get -27 degrees. Now, what does it mean, -27? Is it same as this -27? No, because this -27 is with respect to negative x-axis. And I want here is this theta. To find the theta, then we can see, right, the half a cycle is basically 180. That means from here to there is 180. But it is 27 degrees less than 180, so it's 153 degrees. And that's how you write the theta, because it is 153 degrees relative to the positive x-axis. Finally, part D. So we have a vector which is -2, -1. So for that we have -2 and -1 like this, right? And my resultant vector is this one over here. And this is the theta we're going to be seeking. So inverse tangent will be -1 over -2. And if I find the theta, I'm going to get 27 degrees. Well, but what is this 27 degrees? Because this is also 27 degrees. Are they the same? Of course not. This is a third quadrant. That means you need to understand that this is 180 plus that 27 in order to represent that relative to the positive x-axis counterclockwise. So this is then 207 degrees is the correct way to represent that. All right, so remember, if important that you guys watch these videos ahead of time, and any type of questions you have here, write down, and then you can ask me during the discussion that we have in class. Let's look at another example here. We have a vector A that has a y component, ay equals plus 9.6 meters, and A makes an angle of 32 degrees counterclockwise from the positive y-axis. What is the x component of A? And what is the magnitude of A? All right, so let's draw this vector. This is x, this is y. So we are told that this is its y component. So as a value of the magnitude, we're only given the y component magnitude, which is this one over here, let's say. But we have then the vector A is 32 degrees counterclockwise from the positive y. That means this is my vector A. This was AY. Okay. This is 32. Okay. Now, what is the x component? Well, one thing I know here is this x component will be this vector here, right? Pointing in that direction. So this will be AX. And from here, I can look at it and I can see that the x component is the opposite in this triangle. Y component is the adjacent in this triangle. And I am given the y component. So this is plus 9.6 meters. And I'm given the theta. So then for part A, I can use this tangent of theta that, remember, relates opposite and adjacent. Adjacent, which means opposite is, in this case, x component, and adjacent is y component. That means x component here is just an y component times tangent of theta. AY component is 9.6. 9.6 meters, then tangent of 32 degrees. If I do that calculation, I'm gonna get 6 meters. All right, but I know one thing, that x component is pointing to the left because it's the second quadrant. So technically then I put negative 6 meters. All right, let's look at part B. What is the magnitude of A? Now, there are a number of things I can do here. I can say, all right, A is the square root of AX squared plus AY squared. Since I have now AX and I have AY, I can just go ahead and solve this. But I can also do this. Remember, sine of theta is AY, well, in this case, actually AX over A. I can also say A is equals to, well, AX over sine of theta. That also can give me the A. Also, cosine of theta is AY over A. Again, because AY here is adjacent to that triangle. Then A here is AY over cosine of theta. That means I have 1, 2, 3 ways I can find the magnitude. And then just choose which one you want to do. Let's say any of them will give you 11.3 meters as an answer. Okay, whatever method you choose. All right, so let's continue. Okay, so if a component vector points left or down, you must manually insert the minus sign in front of the component, just like I've been doing right now, as done for by in the figure to the right. That means here's a vector. See, if I'm using this angle phi over here, which is kind of like the local angle with respect to that adjacent and opposite sides, right, for that triangle, then let's say for example, this is 20. Okay, so if I'm using that, I'm going to get positive values. But I understand this vector B is in 4th quadrant and y component should be negative. Okay, so then let's say, for example, this is 10. Then I can say by is equals to 10 cosine of 20, which technically will give me a positive value. In order to avoid making mistakes, you just manually put the negative. Okay, so now that means this is, what you should always do if you're given theta with respect to some of those local coordinates, right? In this case, in negative y-axis. You can avoid doing this, for example, by taking the theta always, or the angle of this, or the direction of this vector always with respect to the positive x-axis. So for example, hopefully you guys also noticed that because of this angle phi is given with respect to, let's say, the negative y-axis, x component is in terms of cosine, y component, x component is in terms of sine, y component is in terms of cosine. That's because the x component is the adjacent, the opposite to that phi. And then the y component is the adjacent to that phi, okay? Now, here's then one thing we can do. So let's say I take that vector b, for example, and put it in the coordinate system, right? So let's say here's that vector b, right? So I move it toward the origin. Instead of using this phi to represent the direction of this vector b, I'm going to use this as a theta, that theta to represent the theta of b. What is the theta of b? Well, theta of b, I know one thing, that from here to there is 270. So it will be 270, then whatever that phi is, 270 plus phi. Then I can represent the direction. Because think like this, if this is 20, then this becomes 290 degrees, right? And that's basically accurate, for that vector. So it doesn't matter if I say 20 with respect to negative y-axis, or I say 290 with respect to positive x-axis, that's exactly the same vector. Here's the advantage of, using this sometimes. If I do that, then for b, I get this. X component then will be b cosine of that theta. And then the y component will be b sine of that theta. And again, this theta here is this theta with respect to positive x-axis, counterclockwise. I don't even have to manually put any numbers, because for example, if I do 10, right, cosine of 290, what I'm going to get here is this. Plug it in your calculator and see. 10 cosine of 290, I'm getting 3.4. And if I do 10 sine of 290, I'm getting negative 9.4, which means I didn't need to manually put the negative for the b. It's part of the equation, and I get it, directly, automatically. See, if I used b, for example, right? Let's say by is equals to 10 here, right? Cosine of 20. If I do this, what I'm gonna get here, plug it in your calculator, you will see you're gonna get 9.4, not negative 9.4. So that's why you have to manually put the negative 9.4. All right. But if you're using this method, taking the direction of the b to be with respect to positive x-axis, right, counterclockwise, then the x component is no longer in terms of sine, because it's independent of, let's say, that opposite and adjacent. So x component always in terms of cosine, y component always in terms of sine, and you don't have to manually put any negative or positives. It will automatically take care of that. Basically, another way you can solve this problem, another thing you can do. It's up to you if you want to do that. Sometimes I do it, sometimes I don't, but I'm used to that. So whatever you are comfortable with. If you want to start with, you can choose one of them that you think is easier, and then use that, and maybe mix it up a little bit as you go. Okay. So here's one example. So this example is basically shows us to how to find a resultant by adding two-dimensional vectors. That means we're going to use everything that we just learned, right? All of those component methods and things like that we're going to be using to find the resultant. All right, so it says you have a vector A, which is technically here. This is that vector A. This is that vector A, our original vector A. Has a magnitude of 40 meters and points in a direction of 20 degrees below the positive x-axis. So that's right, 20 degrees below the positive x-axis. A second vector, B, has a magnitude of 75 meters and points in a direction of 50 degrees above the positive x-axis, which is this guy over here. So we're going to sketch A and B. So let's say those are A and B. And then we're going to do sum of A and B, A plus B, which means that I can, use tip to tail. By the way, let me tell you this. If I'm doing A plus B, which moves B to the, tail of B to the tip of A, I can also go other way around to do B plus A, where I keep B, same place, and I move A, where tail of A connected to the tip of B. Same thing. You're going to get exactly the same thing. So let's say here, I take B and I move it here, where so you can see, right, tip to tail of A connected to the tip of B. And then the resultant will be from your starting point to your end point. Okay. So then the diagonal line is then vector C. Okay. Here we have this vector C. Put it back. So here's vector C. And this is A plus B or B plus A. This, what I did right now is the sketch of this resultant vector. Okay. But it also gives me a lot of information, which we can estimate. For example, look at the length of vector C. The length of vector C, from my graph, is actually longer than A or B. That means longer than B, and B is 75 meters. That means you can estimate. So for example, I can estimate the magnitude of B to be a little bit longer than B. So the magnitude of C to be a little bit longer than B. B is 75, and I would estimate, and you can try to estimate too, I would estimate to be this maybe, I don't know, maybe 90, right? So slightly longer, so roughly about 90 meters. Theta, let's estimate. See, this is, I know that the vector B here is 50 degrees. And this is vector, this is vector C, which is, less than even half of that distance, right, at that angle. So I estimate this to be roughly 25 degrees, let's say. Again, give or take, right? There are uncertainties. So maybe, I don't know, plus minus 5 meters, plus minus, let's say 5 degrees. Why not? All right, so maybe here I can be a little more accurate and maybe say plus minus 3 degrees. Okay. So, excuse me. Those are my estimation. Not precise, but estimated values of the graph. Then in order for me to use, for part B, right, it says using the component method of vector addition, find the magnitude and direction of vector C. And this is where I'm going to show you that 4-step approach to solve any type of calculation of vector addition like this. Step 1, we already did that. Find the, do the graph and maybe graphically find the resultant. That's step 1. Step 2 will be to make a table. We call it the vector table. And here I have my vectors. What are my vectors? I have vector A. Remember, I'm looking at the original vector A. So this is my vector A. And I have vector B. And I know that if I add those two vectors together, I'm going to get vector C. But I cannot just do that directly. Remember, we talked about that, hopefully. Hopefully you know that. What I need to do here is then make 2 more columns, which is X component of my vectors, another one which is Y component of my vectors. So then I look at each one separately. Here's vector A. What is the X component of vector A? So I just put it there. Well, I can see that A has a theta of 20 degrees with respect to X axis. So I can say that this is just A cosine theta A. Then this becomes A sine of theta A. In which direction the vector A is pointing, or which quadrant it is? Quadrant 4. What are the component signs? Well, X is positive, but Y is negative. I just manually put those because I'm using that 20 degrees, not, let's say, 360 minus 20. If I use 360 minus 20, which is 340, right, I wouldn't have to put the negative manually. How about vector B? Well, I can see that B is with respect to the theta, with respect to positive x-axis. So if I break them down, I'm going to get like B cosine of theta B here and B sine of theta B here because the theta with respect to positive x-axis. First quadrant, so plus plus. That means what I get here is this. So this column, second column is the X component, including the X component of X. That means if I'm doing here A plus B to get C, then I'm going to get X component of A plus X component of B to get X component of C. Same thing, I'm going to then do some of the Y components to get CY. That means this is going to be your vector table. So I call this vector table, which organizes very carefully all of your vectors and its components. Then step 3 will be to use this table to get what Cx and Cy are. So you get basically a pair of equations. Equation 1 gives you what the x component is, which is then technically sum of the x components of your vectors. And my x component of A is A cosine theta A plus B cosine theta B. A is 40 meters, then cosine of 20 degrees plus 75 meters, cosine of 50 degrees. And if I do this calculation, I'm going to get the magnitude of the x component. Okay. So I'll get this 85.8 meters. If you do that calculation, you're going to get 85.8 meters. Then we have equation 2, which is the y component. So AY plus BY, which will be then negative A sine of theta A plus B sine theta B. Negative 40 meters sine of 20 plus 75 meters sine of 50 degrees. I calculate, we're going to get 43.8 meters. That means the goal for step 3 is to find then the components of this resultant vector C. All right? Because now we know if I have the components, step 4 going to allow me to use the magnitude, to use them to find the magnitude and the direction of the resultant vector C. Equation 3 gives you magnitude of vector C, which will be x component of the C square plus y component of the C under the square root. 85.8 meters square plus 43.8 meters square. I add them together, find this to be 96.3 meters. There you go, which kind of matches what I have. So, maybe my uncertainty, I should have probably put like plus minus 10, but it is a little bit more than, let's say, what I predicted. I predict 90 plus 5, but this is 96, but still close enough, right? And equation 4 gives you then the direction, theta C, which will be then inverse tangent of y component, 43.8 over x component, 85.8. And if we calculate this, I'm going to get 27 degrees, which matches with my prediction about roughly 25 plus minus 3, right? And that's what we do. We have to use this, if you use this approach, right, you can never go wrong. You will minimize all the mistakes. You do the graph first, then you make a table with all of your values, all of the x components and y components very carefully, identify each, the direction, put the negative here, whatever it's negative direction, right? And organize everything in the table. And then step 3 gives you those 2 equations to find the components. Step 4 gives you the last 2 equations to find the magnitude and direction of the resultant. If you master this approach, then whenever we go to chapter 5 and 6, you're going to get much easier time, because when you're doing the net force, when you have an object, you have a lot of forces acting on them, to find all the net forces, just basically doing what we're doing right now, is to calculate the vector sum. All right. Here's another example. All right, so a disoriented physics professor drives 3.25 kilometer north, then 2.2 kilometer west, and then 1.5 kilometers south. Find the magnitude and direction of the resultant displacement using the method of components. In a vector addition diagram, roughly to scale, show that the resultant displacement found from your diagram is in qualitative agreement with the result you obtain by using the method of components. That means we have here's the graph for your 3 vectors. Let's call them A, B, and C. You can see, right? I can write A, 3.25 kilometers north, B, 3.2 kilometer west, C, 1.5 kilometer south. And I draw all those vectors, connect them tip to tail, and here's the resultant. That's my resultant vector. Now, what do we get from the resultant? Again, you can estimate some of the things, right? So you can estimate in terms of what do you have for this resultant? What do you think would be then, approximate, like let's say estimated values for the magnitude and the direction? Okay. Again, you can just basically estimate. For example, when I look at vector R, I can see that vector R is in the second quadrant, which means I estimate that when I find its components, X component should be negative, Y component should be positive. We should verify that. That means Rx should be basically negative and Ry should be positive. That's, how I represent positive, negative, let's say. Also, look at the size of R. If I compare it to the other ones, R has a size that is shorter than A, but longer than B. Shorter than A, longer than B. A is 3.25, B is 2.2. So I estimate for this to be somewhere between them. So I can estimate the magnitude of R roughly, I don't know, maybe 2.8 or something like that, right? So 2.8 or maybe like 3.0, something like that. So plus minus, let's say, plus minus 0.4, let's say. Also, I have direction for the R. Let's see. Remember, direction is this, right? So this is the direction relative to positive X. I estimate this since, this is 90 degrees, about half of that. So I would imagine it's, I don't know, roughly 100. So you can see, right? If this is 45 and this is 90, then 90 plus 45, so 135. So I estimate this to be roughly that. We'll do the calculation and we can verify, but this is what I roughly, estimate to be. All right, then let's do this. This was your first step to do the graph. Second step will be to make a table. With a table, then we can write down all the values. So I have my vector A, my vector B, and my vector C. And when I add them together, right, I'm getting the resultant. But in order to get that, what I'll need to do is to first find the, basically X components, right, of each one. So X component of A, B, and C, and things like that. So let's say here's AX, here's BX, here's CX, here's AY, here's BY, and this is CY. And what I get are the components of the resultant. Let's see what we have for, those values. AX is an X component of vector A, but A is only pointing toward the positive Y direction, which is north. So it has no X component, and its Y component is the same as A itself. X component of, B is, pointing in a negative direction, so negative B, and it has no Y component. Vector C has no X component, and it's pointing in a negative, in negative Y direction, so it's basically negative C. Okay, and that's what we get. Then step 3 will be to get my equation 1, where Rx equals AX plus BX plus CX. Well, this is 0 minus B. Remember, B was 2.2 kilometers. Then minus plus 0. That means X component is nothing but negative 2.2 kilometers. And remember, I estimated the X component to be negative, and that's what I got. Equation 2 gives me then Y component, which is basically A, again, AY plus BY plus CY, right? So I ended up doing A plus 0 minus C, which is 3.25 kilometers minus 1.5 kilometers. So then the Y component for, resultant vector is 1.75 kilometers, which is the Y component positive, which again, what I predicted. All right, so I got the direction, I got the components of the resultant, X and Y components. Then step 4 will be to use equation 3 to find magnitude of R. In this case, it will be square root of negative 2.2 square plus 1.75 square inside the square root. We find the magnitude, 2.81 kilometers. And roughly matches what I predicted. Then find the direction, inverse tangent of y over x, so 1.75 over negative 2.2, and I will get then the direction for this resultant vector. See, now if I do that, which is 1.75 divided by negative 2.2, I'm going to get negative 38.5. Let's say negative 38.5 degrees. What does it mean, negative 38.5? Remember, it means that what we're finding here is this. By finding the components, we basically found the Rx, which is here, and Ry, which is there. And then using the tangent, we find that angle. That's why it's negative. It's clockwise from the negative x-axis. But what we want here is we want this theta over there, which will be nothing but 180 minus 38.5. So this will give us 141.5 degrees with respect to positive, which is again roughly what I kind of estimated. Okay, so magnitude and direction, that means, you know, we have an extra step over there to represent it as 141.5 degrees, right? 180 minus that. Okay, so that's the direction and magnitude of the resultant vector. All right, I told you in the beginning that there's an easy way of representing directions of vectors instead of saying plus x, minus x, or, you know, let's say east, south, north, things like that. So in order to do that, we're going to learn about what we call unit vectors. Unit vectors are vectors, just like, you know, unit represents, right? Unit means like, you know, magnitude of one. So the unit vector is, for example, one vector pointing along the x-axis, has a magnitude of just one, no units, just one as a magnitude, and its direction in the positive x-axis. It means we, you know, label this as I hat, and this I hat is basically a vector that only pointing in a positive x direction with a magnitude of one. So you can see, right, each vector is a magnitude of one, no units, and parallel to the coordinate axis. A vector with this property is called a unit vector. So here's one of them, I hat. So this is a unit vector with one magnitude. That's why it's unit, right? Unity. It's in a positive x direction. We can same way have a vector, unit vector along the y-axis, and we designate as a j hat. Again, the unit, you know, the unitless with the magnitude of one pointing in a positive y direction. Okay. And what we can do here is that we can use these unit vectors to give any vector a direction. Because if I have vector A, and if I multiply this vector A by the I hat, then this is just basically what it does. It gives the, multiplies this by one, which in no way changes the magnitude of vector A, but then it easily, represents the direction of this vector A. If let's say it's a horizontal, that means we can use these vectors to establish a direction. Okay. One thing I have here is, for example, if the direction of my vector is pointing to the left instead of to the right, I can then use negative I hat to represent direction, because I hat means positive X. By putting negative I hat, remember, we're just basically changing the direction of vector I hat. That means here's what I have. Every time I take a vector, vector A, and whenever I break down into components, then I can say this X component as a vector is equals to its magnitude, AX, times unit vector I hat. So, and I can write this vector AX as magnitude IX times I hat, because it says this is my magnitude, this is my direction, which means it's a horizontal if it's I hat. Magnitude is just basically how big the vector, A is. Same way, I can represent the Y component in terms of AY J hat, because then instead of writing this as a vector format, ax vector plus a y vector, I can say it's ax magnitude of ax times I hat plus magnitude of ay times j hat, which tells you then also in which direction are they, okay? Because this is, if I have, you know, ax I hat plus ay j hat, and if I look at this vector, I know one thing, that this vector has both x and y components. If, for example, I have a vector b, and this is just, you know, 5j hat, that means this is a vector with 0 I hat. It's just basically, you know, only 5j hat, means it's a vector along the y-axis. There's also an x-axis, and that vector here is k hat, which is in a positive z direction. That means in a way we can have a, you know, three-dimensional, which we'll learn in the next chapter. And this is basically, you know, az k hat, something like that. So k hat is for the z-axis. All right. That means any vector, now if you break it down into components, you can write this in terms of, you know, horizontal components coupled with the I hat unit vector, and a vertical component coupled with a j hat vector. And it's a much easier and cleaner notation. So I suggest you guys learn this really well and always use that, because whenever we're doing the calculation and things like that, you can see, right, any two things that have I hat, you can add them together. Any two things that have I hat and j hat, you're stuck, you can't add them together. So that's why it's like easy to see, right, which ones can be added, which ones can't be added. Also, one of the things we have here is, remember we talked about that in the previous chapter, right? Whenever you have an incline, it's convenient to tilt your coordinate system as well. So for example, if, you know, if you imagine there's an incline with this angle theta, right? Or, you know, let me do it, you know, in terms of, for example, this is my coordinate system, right? And this is some theta. We can then kind of tilt our coordinate system a little bit, okay? So, and if I do that, the axes are still perpendicular to each other, but there is no requirement that the x-axis to be horizontal, okay? So that means sometimes we need to, let's say, tilt the axis depending on what we have. And, you know, we'll be doing a lot of those type of, you know, let's say, examples where, you know, instead of, for me, like, let's say if I have that vector and I choose this as my coordinate system like that, then I'm taking, you know, two-dimensional vector C, and when I break it down into components, you know, like let's say, right, I get two-dimensional vectors, which, you know, makes no sense. So easier just to take the, you know, and tilt my coordinate system such that horizontal is still along the horizontal and vertical still along the vertical. All right, so tilted axes are useful if you need to determine the components vectors parallel to and perpendicular to an arbitrary line or surface. Okay, and we are free to do that. We will see that, you know, especially when we get to the next chapter, right? When we have like two-dimensional, three-dimensional, you know, vector calculations, then we can actually do that. Right. So we have here one more example. Right. So, and this is basically finding the sum of two vectors, but we're now given them those vectors, right, in terms of their components. So here's vector A. By the way, the bold version of that, it also means that it's a vector. So you can either do A with the arrow on top or just make the A as bold. In math calculus classes, that's what we usually do for the vectors. So that also means it's a vector. So this means this is a vector A, and vector A has 4i hat, 4i hat, which means this is the, you know, remember, if I write it as ax I hat plus ay j hat, means that this is basically nothing but the x component of vector A, and this is the y component of vector A. Same with the B. Okay, so let's say we are given those two vectors. For part A, we want to find then the magnitude of each vector. That means if I take vector A and I write it down, 4i hat plus 7j hat, I'm basically saying that x component here is 4 and y component here is 7. Then I can find the magnitude of A by taking the square root of the x component square plus y component square. Plug in the values of those basically, right? All right, so if I do that, then I'm gonna get 8.06 meters. Well, there are no meters, sorry, no units. 8.06 for the magnitude of A, which is, you know, a squared plus, you know, ax squared plus ay squared. Same with the vector b. I have 5i hat minus 2j hat, which means the x component of b is 5, and the y component of b here is negative 2. And if I'm finding b, it will be basically 5 squared plus negative 2 squared, and that will give me 5.39 for the magnitude of b. All right, so that's kind of what we have. Then it says use the unit vectors to write an expression for the vector difference a minus b. Okay. Now, here's then one thing we can do. Remember, what we're saying here is this. So let's say resultant vector is equals to a minus b. And here we can look at a little bit different approach, right? So one thing we can do, we can remember make a table. So a, b, and this is r, right? So these are my vectors, x component, y component. And then here I have my components. So remember that this was 5 and sorry, this was 4 and 7, all right? And this was 5 and then negative 2. And the idea here is to find the r, but what we're doing is a minus b to get that, right? So I can say then it's 4 minus 5 and 7 minus negative 2. That means the rx component here will be 4 minus 5, so it will be negative 1, right? And 7 minus minus 2 will be 9. This is for the ry component. So you can see, right, this table basically allows you to, sorry, not negative 9, it's positive 9, allows you to get that. But additionally, you can do it like this. So a minus b, what we have for a is 5i hat plus, oh, again I do that. So 4i hat and plus 7j hat. Then this is plus, sorry, minus vector b. What is vector b? Vector b is 5i hat minus 2j hat. So technically I have this, 4i hat plus 7j hat minus 5i hat, then plus 2j hat. Remember, what we can do here is we can add things that are I hat and add things that are j hat together, but not I hat and j hats together. So I have then things like this, 4i hat plus 7, sorry, minus 5i hat, they're together, then plus, then I have then 7j hat, then plus 2j hat. Okay. So then if I do that, well, let me make sure that you guys, so this is minus minus 2, so that's why it ends up like that. But in any case, so if I calculate this, those two together gives me negative 1 I hat, plus those two together give me 9 j hat, which means that x component and y component, you can also find it like this, just like we did from the table. That means just another way of basically finding that, right? So you can do this in terms of this, this version. That means vector r is equals to, if it's a minus b, you can just write it in terms of components, right? The general is that ax plus ay, right? So ax I hat plus ay j hat, then minus bx I hat plus by j hat, and then continue from here and open it up, and then just add x components, I hat components together, and j hat components together. Anyway, so that's what we got for the r hat, sorry, the r vector. That means we know that r vector here is two-dimensional vector. There's a negative x component, negative 1, for rx, and a positive y component, which is 9 for ry, which, again, we calculated from here as well. All right, so then we also needed to find the magnitude and the direction of this vector. And I can find the magnitude by using the components. So negative 1 square plus 9 square, and I can find this to be 9.06. And then do inverse tangent of 9 over negative 1. So then we get you know, the direction, right? Negative 83.6 degrees. And the reason that we get this, because there's a negative x, positive y, which means that this guy here is somewhere over there, right? So maybe even something like this, somewhere over here. And we're finding this angle theta there. So then what we do here is we finally find the theta relative to positive x, so which will be 180 minus 83.6, and this gives us 96.3 degrees. That means this is what we want, 96.3 degrees. So magnitude and the direction of the resultant. You can see, right? So we're pretty much doing the same thing. We're using the component approach to find all that. All right, guys, so that's it for this chapter. Then in the next chapter, we'll then be using all of this to look at some two-dimensional problems, because the things that we're going to be covering in chapter 4 are two-dimensional vectors like acceleration and velocities.